So, we will continue our discussion on IC engine. Today we will discuss about a comparison between the cycles that whatever that we have discussed in my last lectures, the Otto cycle, diesel cycle and dual cycle, and at last we will discuss about that when we talk about actual cycles, we have approximated different cycles like Otto cycle, diesel cycle and dual cycle using air standard analysis. Rather, we have invoked air standard analysis only to have a mathematical quantification of thermal efficiencies. So, we will now see that the process which is occurring in a real engine, real internal combustion engine, maybe is not actually same what we have approximated in a air standard analysis while we are trying to obtain the mathematical expression of thermal efficiency. Now, before we go to discuss about the difference between the approximations, maybe we will discuss that while we are approximating different cycles using an air standard cycle, maybe Otto cycle, dual cycle and diesel cycle, and we are approximating that okay fine, whatever processes are there in internal combustion engines are represented by isentropic compression, then constant volume heat addition or constant pressure heat addition, then isentropic compression and constant volume blow down. Those processes are not exactly same what is there in a real internal combustion engine, and since these are approximations and sometimes these approximations leads to some error while we are calculating thermal efficiencies. So, that means while we are calculating thermal efficiency of a cycle from using an air standard analysis, maybe we are underestimating the thermal efficiencies, and that is what we discuss in detail today. So, before we go to discuss about those aspects, let us first discuss about a comparison of thermal efficiencies of different cycles. That we have discussed that Otto cycle, dual cycle and diesel cycle. We have discussed that for a given compression ratio, efficiency of the Otto cycle is higher than the diesel cycle, and also we have discussed that since the compression ignition engines, CI engines are normally operated at a higher compression ratio, of course compression ignition engine will have higher efficiency compared to the SI engines. But and that is why we have commented that the constant volume combustion is more efficient than the constant pressure combustion, and for that in a dual cycle we have seen that the entire combustion process is split into two different parts. First part of the combustion is approximated by a constant volume heat addition, while the second part of the combustion is approximated by a constant pressure heat addition, and we have calculated thermal efficiency through a rigorous mathematical analysis. Okay. So, without going into the mathematical analysis of thermal efficiencies of different cycles, only from a PV and TS diagram, we would like to have qualitative comparisons of thermal efficiencies of different cycle. So, today we will discuss about comparison of Otto, diesel and dual cycles. So, we will do this. So, now again I am telling, without looking into the mathematical expression of thermal efficiencies of Otto cycle, diesel cycle, dual cycle, here we will try to quantify, of course qualitatively, the efficiencies, the order of efficiencies of different cycles only from a PV and the corresponding TS diagram. So, while doing so, we need to have while we are trying to have a qualitative comparison between among Otto, dual and diesel cycles, we should have a common basis for the comparison. We cannot have a comparison without having a common basis. So, that means I would like to say that without looking at the mathematical expression of thermal efficiencies of different cycles, just only having a look at PV and corresponding TS diagram, we can quantify, rather we can have a qualitative estimate of the thermal efficiencies of different cycles, rather we can predict the order of efficiencies of order of thermal efficiencies, and to do that we should have a common basis for comparison. So, as a common basis for comparison we might have two different cases. As a first we have two different cases. As a first case, rather case A. So, while we are having comparison of Otto, dual and diesel cycle, to have a common basis for comparison, as a first case we have same peak pressure rise, same compression ratio for all three cycles, I mean Otto, diesel and dual, and as a second case, case B, we have another common basis for comparison, that is same peak pressure. So, these two are the common basis. For the first case, while we are trying to have a qualitative estimate of the order of efficiencies of three different cycles, we will keep constant, that we will keep the compression ratio is same for all three cases. As a second case, we will consider that the peak pressure is same for all three different cases. So, now we would like to discuss the first case, that is when compression ratio is remaining same for all three cases. So, if we consider case 1, case A, that is same compression ratio. So, for the same compression ratio, if you would like to obtain the thermal efficiencies of Otto, dual and diesel cycles, we have to draw PV and TS corresponding TS diagram. Since we are not interested to look at their mathematical expression of thermal efficiencies. So, if I try to draw PV and TS diagram, so this is the P and V diagram. So, compression ratio will remain same. So, I mean what is compression ratio? Let me discuss again. Compression ratio we have discussed very beginning of this course, that is compression ratio, that is R equal to V BDC by V TDC. So, while you are trying to have a comparison keeping compression ratio same for all three different cases or three different cycles, we need to ensure that the compression and expansion will take place between the same compression ratio, that is V BDC and V TDC is fixed for all three cycles. If that is the case, let us first draw the, say this is V TDC and this is V BDC. So, this is the air intake process, let us say process, I mean process is 6 to 1, that air intake process at constant pressure. Next process is isentropic compression. So, this is isentropic compression. So, maybe process 1 to 2 is isentropic compression. Then we have a Otto cycle, that constant volume heat addition, combustion is represented by constant volume heat addition. So, maybe this is the peak pressure, then we will have isentropic expansion, then we will have isentropic expansion, and then this is constant volume blow down or rejection. So, maybe this is 3A, that is Otto cycle. So, if the compression ratio is remaining same for diesel cycle, then maybe this is 3B, maybe this is 3B, this is the diesel cycle, and if it is a dual cycle, then a part of the combustion is completed at constant volume process. So, maybe this point is X and this point is 3C and this is 4, this is 1. So, if I write over here that the Otto cycle that is 1, 2, 3A, 4, 1 and finally 1 to 6 is the, or 5 to 6, if it is 5 to 6 is the exhaust. constant pressure exhaust. So 1 2 3 4 1 the Otto cycle. Then if I try to plot diesel cycle, what is diesel cycle? 1 2 3 B 4 1, this is diesel cycle, and next is a dual cycle. Dual cycle is 1 2 X 3 C 4 1. So these three are different cycles that what we have plotted in a PV diagram. If I would like to plot corresponding TS diagram, that is a very important diagram. From there we should have a, I mean, qualitative estimate about the thermal efficiencies of three different cycles, that is what we have plotted in PV diagram. So this is TS diagram. So now question is, 1 2 is isentropic compression, that is there for every cycles, that is Otto, diesel and dual, whatever it is, that is there every cycle. So process 1 to 2 is isentropic compression. So this is 1 2, this is isentropic compression. Then of course 2 to 3A is the peak pressure, of course temperature will be higher. So this is 3A, so this is 3A, and then we first draw the Otto cycle, the processes in Otto cycle we have drawn in PV diagram, corresponding processes we will draw in the TS diagram. So 1, so this is 4, this is 3A. So 1 2 3A 4, that is the Otto cycle, that is what we have seen in PV diagram. So this is the corresponding TS diagram. Now 2x, so this is x, then 3C, and then this is 3B. So 3B 1 2 3B 4, because temperature at point 3B should be less than temperature at point 3C. This is the point from where we can draw the corresponding TS diagram. So we have drawn. Now question is, we have seen, rather we have discussed that the area under the process line in TS diagram gives the heat transfer. So similarly what we can see, area under process line 4 1 gives the process line 4 1 in on TS coordinate or TS diagram on temperature entropy coordinate. Gives heat transfer rather heat rejection from the system. So what we can see, that for all three different cycles we have plotted in PV and TS diagram, process 4 to 1 is the exhaust or rather blow down, constant volume blow down. So if we try to draw the area under the process line 4 1 on TS plane, so then this will give the heat rejected from the system. So what we can conclude from this diagram, that the heat rejected from the system is remaining same for all three different cycles, since process 4 1 is same for all three different cycles. So maybe Q out is same for all three cycles, but Q in, that is heat being added into the system, that is different for three different cycle. From this TS diagram we can see that Q in is the area under process line 2, 3A on TS coordinate, on TS area under process line 2 to 3A on TS coordinate. This gives the heat being added into the system for Otto cycle. So this is for Otto. Similarly Q in for diesel is equal to area under process line 2, 3B on TS coordinate. and Q in for dual is equal to area under process line 2 comma 2 stroke x stroke 3 2 dash x dash 3a on TS coordinate. So, what we can see from this, that the heat rejected from all three different cycles is same, but the heat being included, rather heat being added into the system because of the combustion is different, because area under the process lines are different in the TS diagram. So, we can say that Q in dual is less, sorry, Q in diesel or Q in auto is greater than Q in dual greater than Q in diesel. So, this is the case. So, Q in auto greater than Q in diesel, dual greater than Q in diesel, but Q out is same for all three different cycles. So, now if we try to look at the thermal efficiencies, so in general the thermal indicated thermal efficiencies irrespective of the cycle, whether it is DL, dual or auto, is 1 minus Q out divided by Q in. Q out is remaining same for all three different cycles, while Q in is changing. So, Q in is higher for the auto, then dual, then diesel. Then we can say the thermal efficiency of the auto will be greater than thermal efficiency of dual greater than thermal efficiency of diesel. So, this order we are getting due to the change in heat being added into the system, which varies from auto to dual to diesel. Now, this order we are getting essentially for a case when we are keeping compression ratio same for all three different cases. So, that is eta greater than eta or T auto greater than eta T dual greater than eta thermal diesel. So, this is the case for a case when compression ratio is same. So, for a same compression ratio, efficiency of the Otto cycle is greater than efficiency of the dual cycle greater than efficiency of the diesel cycle. Of course, we have seen, at least we did not discuss that whether efficiency of the Otto cycle will be higher than the dual or not, but we have discussed from the expression of mathematical expression of the thermal efficiency of Otto and diesel, that for a given compression ratio efficiency of the Otto cycle is higher than the diesel cycle. So, that is what we have seen from another perspective, that is from a look at the TS diagram. Next case, before going to discuss about the next case, that is while we are keeping the peak pressure same for all three different cases. See, compression ratio same, keeping compression ratio same, rather consideration of same compression ratio as a common basis is not an ideal case. Rather, I mean, this is very difficult to have a same compression ratio for all three different cycles. To be precise, compression ratio of diesel cycle is always higher than the dual and greater than the auto, because diesel engines are always operated with a higher compression ratio. So, while we are trying to find out the order of thermal efficiency of three different cycle considering compression ratio same, it is not an actual case. So, it is always better to consider different other aspect to be the common basis for comparison, and for that the peak pressure same is, that is what we have discussed as a second case, that is the most realistic one, because peak pressure same, if we need to fix it for all three different cases, then it is very realistic, rather it is a very actual case, because the peak pressure is very important, because it is a very actual design limitation in all three engines, in a real internal engine. So, that is what I am telling. that same peak pressure, so this is very important. The compression ratio same, we have tried to estimate the order of thermal efficiency, that is fine, but the compression ratio same is not the actual case, because compression ratio will vary from one cycle to other. But if we try to keep peak pressure same for all three different cases, that will be the actual case, and it is more realistic, because the peak pressure is the actual design limitation in most of the internal combustion engine. So this is the most actual case, because it is very important, because peak pressure is the actual design limitation. Very important, because as I said you that engine cylinder acts as a pressure vessel. So whenever we are having higher pressure, maybe at the end of the compression, then we are having combustion. So due to the combustion we will have temperature, since in case of Otto cycle we are approximating constant volume process, so pressure will go high. And also in case of a CI engine, although we are having constant pressure, but still we trivially cannot ignore that the rise in temperature will leads to a rise in pressure as well. So the peak pressure that the engine cylinder needs to withstand during the process of combustion is the actual design limitation. This is actual design criteria. So and for that, consideration of same peak pressure while considering the order of, rather while considering the efficiencies of three different cycles would be the most realistic one and would be the most actual case. And considering that, next we will discuss that what will be the order of thermal efficiencies of three different cycle if we consider same peak pressure. So next case, that is case B, is the same peak pressure. So this is the same peak pressure. So this is the most actual case. So if you would like to consider same peak pressure and what will be the PV and then corresponding TS diagram, then you need to look into it. And I would like to emphasize over here that while considering same peak pressure, it is not mandatory that we have to keep compression ratio same. Rather, compression ratio will change, and that is what is most important for all three different cycles, because compression ratio is no longer remain constant or same for all three different cases. So if I try to draw PV and TS diagram, so this is PV and PV diagram, then we may have same peak pressure. So maybe this is the case, and this is same peak pressure. So maybe this is BDC. So this is the process of maybe intake, constant pressure intake, then we will have a isentropic compression. Maybe this is 6, this is 1, this is 2, then we will have a blow down. So maybe this is 4 and this is 3. So 1, 2, 3, 4, that is the diesel cycle that we can see from the PV diagram. Now what will be the Otto cycle if you try to superimpose on that same PV diagram? We have drawn the PV diagram for the diesel cycle. If you would like to superimpose the different processes on the same PV diagram that is there in an Otto cycle, then the cycle will be like this. Maybe 1, this is 2A, that is 1, 2A, 3, 4, 1 is the Otto cycle, that you can see that because combustion is again represented by constant volume heat addition. Similarly, if you would like to represent dual cycle on the same PV coordinate, then probably this will be the case. Maybe this is this is 2B and this is X. So 1 comma 1 2a 3 comma 4 is the Otto cycle, 1 2b x 3 4 is the. So if I write that Otto cycle 1 dash 2a dash 3 dash 4 dash 1, diesel cycle, that is what 1 2a 3 4 1, and dual cycle, that is 1 2b x 3 4 1. So these three are the different processes we have identified in the same PV diagram, and we can see from the PV diagram that VTDC for Otto. So this is VTDC for dual and this is VTDC for diesel. So we can see from PV diagram that the VVDC is remaining same for all three different cycles, but VTDC is changing. VTDC is less for Otto and then dual and then diesel. So since VTDC is changing, so definitely the compression ratio will change, and as I said you that the VVDC by VTDC is a compression ratio. So VTDC is less, definitely compression ratio for the CI engine will be higher, and compression ratio for the SI engine will be less because VTDC is higher than the VTDC diesel. Okay. So now we need to quantify, we need to have a qualitative estimate about the thermal efficiency. So if we draw the corresponding TS diagram, this is very important. So this is T and this is entropy diagram. So what will be the corresponding TS diagram? See 1 comma 2, 1 to 2, this is the isentropic compression and this is 2, and then 2 comma 2 to 3, 2 to 3 is the constant pressure heat addition. Of course this combustion process temperature will rise, and finally you are having 3 to 4 is the this is 3, this is 4. So 3 to 4 is again isentropic expansion. So what about the Otto cycle? So that is 1 2 3 1 2a 3 comma 1 2a 3 comma 4. So maybe this will be 2 i's a, this is 1 comma 2a 3 4, this is the because T3 is the T max, that is because of the combustion, but 2a the temperature at point 2a should be temperature less than the temperature at point 2, and finally we will have, of course temperature at point 2a will be always higher than temperature at point 4, and finally we should have 2b, and 2b will be here. So maybe this is point x, this is 2b. So 1 2b x 3 4 1 is the processes which is occurring in a dual cycle. Fine. So from there again I would say that Q out is the area under the process line 4 1 on TS coordinate, right, and this is same, and Q out is same for all three cycles, for all three cycles. So that means if I try to draw the area under the process line, then Q out is same for all three cycles. So this is Q out, but Q in, that is heat added into the system because of the combustion, is different for three different cycle. Q in is area, the Q in Otto is area under the process line 2a dash 3 on TS coordinate. Similarly, Q in dual is equal to area under the process line 2b comma x comma 3 on TS coordinate, and Q in diesel is equal to area under the process line 2 comma 3 on TS coordinate. So what we can conclude from this, the magnitude of heat being added into the system because of the combustion, that we can conclude that Q in diesel is higher, that is from this TS diagram we can say that Q in diesel is greater than Q in dual greater than Q in auto. So, this is the order what we can see from the corresponding TS diagram. Now, thermal efficiency eta thermal is equal to 1 minus Q out divided by Q in. Q out is remaining same for all three different cases, Q out is same for all three different cases, while Q in for the diesel is higher than the dual than the auto. That means efficiency, the thermal efficiency of diesel should be greater than thermal efficiency of dual greater than thermal efficiency of auto. So, this will be the order of thermal efficiency for three different cycles if we consider same peak pressure ratio. That means we have seen that while you are keeping compression ratio same, that is for a given compression ratio efficiency of the auto is higher than dual than diesel, but what is the most actual case, more realistic case, rather more realistic basis for having a comparison is the same peak pressure, because this is the actual design limitation in most of these internal combustion engines. There we can find that the efficiency of the diesel cycle will be greater than the efficiency of the dual cycle, and that will be greater than auto cycle. Not only that, while you are considering the same peak pressure for three different cycles, we have seen that the compression ratio is, compression ratio for auto is lesser than dual than diesel, and that is what is more much more actual, it mimics the actual case. Efficiency, rather compression ratio of the auto cycle is always higher than the compression ratio of the diesel cycle. So, from there, so we have seen that without going into the mathematical expression, rather mathematical expression of the thermal efficiencies, maybe for dual, diesel and auto, we have at least qualitatively estimated what will be the order for two different cases. As a first case, we have considered the compression ratio is same as a common basis, and although it is not the actual basis, because it is more ideal one, because compression ratio will no longer remain same for all three different cycles. So, this is not the way to compare. So, considering compression ratio same is not the best way to compare thermal efficiencies, and there we have find that efficiency of the auto is greater than dual and diesel. That is what we have discussed maybe in the last class, that for the same compression ratio efficiency of the auto is greater than efficiency of the diesel. But the most actual case is same peak pressure. For that case we have seen that efficiency of the diesel is greater than efficiency of the dual, and which is greater than efficiency of the auto. So, with this we would like to conclude that the comparison of different engines essentially depends upon the heat being added into the system, and that essentially depends upon the combustion. Fine. Now, we would like to discuss that we have considered that we have used that we have approximated different air standard cycle. We have used air standard analysis, rather thermal performance of different cycles, different engines are approximated using an air standard analysis, and while we are doing so, we have assumed air to be an ideal gas, and we have used ideal gas relationship. Now, question is, the actual processes there in an internal combustion engines is not in a true sense the thermodynamic cycle. Rather, I have discussed that we can call it a mechanical cycle. We will now discuss why we can't call it a thermodynamic cycle, rather we are calling it as a mechanical cycle. Because that an ideal air standard cycle which occurs on a closed system and with constant composition. Whatever will be the working substance undergoing the cycle, that working substance, the composition of the working substance won't change. So, and an ideal air standard cycle occurs on a closed system. If you try to recall that in a IC engine, it is not a closed system, because we are taking air and we are compelling out, rather we are allowing combustion product to be compelled out from the system rather through the exhaust stroke. So, whatever combustion product is coming during exhaust strokes, we are not using those combustion product into the cycle, that is cycle is not the path is not cyclic, rather it is not a closed system. And that is why, and as I said you that a composition, and we will discuss that the compositions rather of the working substance will be changed. The composition of working substance will be changed after one cycle, and that too in real engine whatever compositions we are having, I mean whatever working substance is having, it is not following a closed loop, rather it is open. So, that is why an air standard cycle, I mean what happens in internal combustion engine, I mean actual internal combustion engine, different processes. Air standard, if we try to use air standard analysis, rather we have used air standard analysis to have a quantification of thermal efficiencies of Otto, dual and diesel cycle, that gives at best the approximation to actual condition. It is not giving the actual conditions, rather approximations to the actual conditions. That means using an air standard analysis, if we try, we have quantified the thermal efficiencies of Otto, dual and diesel, but in reality the processes that is there in internal combustion engines, those are not in a true sense a thermodynamic cycle, while an air standard cycle, an ideal air standard cycle occurs always in a closed system and with a constant composition. The composition of the working substance won't change, but those are not true for the cycles that we have considered in a real internal combustion engine. That is why if we try to mimic the actual processes in an internal combustion engine using an air standard analysis, I mean that will give at best the approximation to the actual condition, not the actual conditions. Now, what are the major difference? That means real air fuel cycles. So, if we try to consider that real air fuel cycle is not a thermodynamic cycle. So, real air fuel cycle is not a thermodynamic cycle. So, what are the major differences? We have discussed that it is not a thermodynamic cycle, rather we can call it that a mechanical cycle. It is not a thermodynamic cycle, but we call it mechanical cycle. That means the processes in a real IC engine, processes in a real IC engines, internal combustion engines. So, if we try to represent the processes in real IC combustion engine is the processes in a real internal combustion engine is represented, rather I can write, if the processes in a real internal combustion engine is represented by air standard cycle, right, the analysis, the air standard analysis at best will give at best will give only the, rather will predict, at best will predict the approximations, these approximations to actual condition. So, if the processes in a real internal combustion engine is represented by air standard analysis, the air standard analysis, rather air standard cycle, the air standard analysis at best will predict will predict the approximations to actual conditions, not the actual conditions, not the actual condition. So, the Air Standard analysis, whatever we are doing only to have a quantification of thermal efficiencies, that is what we have considered through different processes like isentropic compression, constant volume heat addition or constant pressure heat addition, then isentropic expansion, constant volume blowdown. All these are not, all these processes that what we have assumed using an Air Standard analysis, those are not the same, those are not the correct processes, rather those processes are not mimicking, those processes are not mimicking the actual processes, those are there in a real internal combustion engine, but still we are doing this analysis, and that is why this Air Standard analysis will give at best the approximations to the actual condition, not the actual conditions. And we will now discuss the major differences are. So, what are the major differences? I mean, it is not same. That means the actual processes in a real internal combustion engines are not same what we have assumed while we are doing this Air Standard analysis. The major differences are we have to consider. As a first case, I can tell you, I have discussed that the real air fuel cycle, it is not a thermodynamic cycle. We can call it a thermodynamic cycle if the processes occurring in a closed system with a constant composition. But in real internal combustion engines, it is not a closed system, because you are taking air during intake stroke and at the exit we are getting combustion product. So, air we are getting in fresh air if it is a CI engine, or maybe certain amount of, let us say, very small fraction of fuel, maybe 7% or 5% of fuel with air, homogeneous mixture of air fuel during intake stroke for SI engine, but eventually we are getting combustion product at the exhaust and we are expelling it out into the ambience. So, it is not a closed system. Second thing, compositions. Composition is air at the intake, while composition at the exit is different, the combustion product. There might be carbon dioxide, carbon monoxide, nitrogen, all those things. So, compositions is varying. Not only the inlet gas compositions is differing from the gas which at exit, very often what do we do? In case of a CI engine, air is introduced at the during the intake stroke, but at the late of the compression, what do we do? We try to inject fuel through the fuel injector. That means middle way through the cycle we are changing the composition. So, not only the composition is changing from inlet to outlet. In SI engine, composition is totally changing from inlet to outlet, because at inlet is the only air fuel mixture, at the outlet is different combustion product. Not only that, that is also true for the CI engine, but apart from that, part way through the cycle, what is happening in CI engine, that we are injecting fuel at the late at the compression, and result of which we are changing the composition at the middle of the cycle. So, this is the difference. This is not same. Second thing, during combustion, although the mass is remaining constant, but the quality of the the molar quantity changes. So, although the mass is remaining same during the combustion, but the molar quantity changes, and what we have discussed, that the composition as well as the composition changes, also it is not a closed system. So, this is the one thing, that is the processes in real IC engine rather cycle in real internal combustion engine is not occurring on a closed system. Number 2, composition during composition of the working substance is getting changed undergoing cycle, during cycle. So, these are the one difference, and as I said you that although mass is remaining same, but the molar quantity changes. Second thing, as I said you, so this is one. Number two is very important, that while we are trying to mimic different processes in a internal combustion engine using an air standard cycle, maybe we will be doing, we have taken a few approximations, and those approximations will eventually will eventually introduce error in the calculation. That is what we will discuss. But while we are taking, rather while we are doing that analysis, rather we are doing air standard analysis, we are assuming that the entire analysis is based on the fact that air to be an ideal gas and we are using ideal gas relationship, right. So, in real engine, inlet flow may be air, but maybe up to 7%, the air to be an ideal gas, that is the base the important assumptions, because all the equations we are using isentropic process, that is when you are calculating pressure and temperature at the end of the compression, at the end of the expansion, using ideal gas relationship. So, at the inlet maybe all at the inlet, particularly in case of a CI engine, maybe all air. In a real engine, inlet at during the intake stroke or inlet, it will be all air for CI engine, but in case of SI engine there is a little fraction of fuel, that is 7% of fuel, but at the outlet we are getting a gaseous mixture. I mean we are getting combustion, not the air at all. So, how can you assume that the combustion product, how can you treat that combustion product to be air while you are doing this air standard analysis? So, this is the second question. So, air standard analysis assume air to be an ideal gas. So, air standard analysis assume air to be an ideal gas, and that is what we have seen, because we have used ideal gas relationship to obtain the pressure and temperature at the end of compression and expansion stroke. But if we try to, if we now think about the processes in a real engine, at the inlet during the intake stroke maybe all air, I mean for CI engine, maybe for SI engine a little bit fraction of fuel is there, but in actual internal, in real processes, in actual processes in IC engine, inlet may be all air for CI engine, maybe air plus certain amount of, let us say 7% of fuel for SI engine, 7% of fuel for SI engine, but outlet, that is combustion product. It is having CO2, N2, CO little bit, H2O, etc. How can you assume how can you treat the combustion product to be the air while you are doing the analysis? So, this is one of the major difference, and for which we can't say that the exhaust, rather the combustion product during exhaust stroke will be the air. So, these assumptions, that these approximations of exhaust product as air, so this assumption, rather approximation of combustion product as air, this is very important, simplifies the analysis. So, we are approximating it, that the combustion product to be air, and that is why we have using isentropic expansion, and from using ideal gas relationship we are calculating pressure and temperature at the end of the expansion. but this is an approximations, but the approximation of the combustion product as air may simplifies the analysis, but introduces error in the calculation. That means into the calculation. That means if we use if we use that ideal gas relationship considering combustion product to be air while calculating pressure and temperature at the end of the expansion stroke, maybe we will be doing some mistake, and for there maybe we are underestimating the thermal efficiency of a internal combustion engine. Fine. Number 3 is very important, that isentropic compression and expansion. So, we assume that the process is isentropic expansion and isentropic compression, and we are assuming there is no heat loss. So, there is no heat transfer, but in reality we have seen that engine cylinder should be surrounded by a cooling water jacket, and we should have continuous supply of coolant only to save the engine out of excessive heating. That means we should have continuous heat transfer from the cylinder. If that is the case, how can I assume that the expansion process or compression process to be an isentropic process? It is not possible, because we are having heat transfer, and also we are having frictional losses, because whenever piston is moving inside the cylinder, it is not possible to minimize, it is not possible to trivially ignore the frictional losses, but what we can do, we can minimize, but we cannot make it 0. So, frictional losses is there. Also we are having continuous heat transfer from engine cylinder to the coolant, then how can we assume that the processes are to be the isentropic process? So, this is an approximation. Not only that, while we are doing this analysis, while we are considering that expansion process is isentropic process or compression is isentropic process, mind it that because of this continuous heat and heat transfer, maybe the amount of heat being generated because of the combustion that will be reduced. So, the heat being generated, the temperature rise because of the combustion will be lesser in case of a real internal combustion engine because of the continual heat transfer. If temperature drops, then pressure will drop, as a result of which we will get lesser amount of work output during the expansion stroke than that predicted by the air standard analysis. So, if we try to, that means we have used isentropic relationship, the isentropic expansion ideal gas relationship to calculate the pressure and temperature at the outlet of the at the end of the expansion stroke, but this is not the case in reality, and quantification, rather estimation of pressure and temperature at the end of the expansion process or at the beginning of the expansion process using air standard analysis will underestimate the actual pressure and temperature, rather we will overestimate the pressure and temperature, because temperature which is developed during combustion and because of that pressure that will reduce because of the continuous heat transfer, as a result of which we will get lesser amount of work output from the engine. So, this is the case, and although heat transfer is there, because at the compression, during compression stroke heat transfer is there, that we cannot minimize. I mean but deviation is less because expansion stroke the lower temperature at this time. So, during the compression stroke, since temperature is not that much high at the beginning of the compression stroke, temperature even at the end of the compression stroke temperature is not that much high. So, the deviation is very less, but at the beginning and also at the end of the expansion stroke, I mean temperature is so high, and because of the continual heat transfer temperature will reduce, and it will try to reduce the pressure and we will get less amount of heat work output. So, this is an approximation. Last thing, so their pointer, these points are heat transfer and frictional losses. So, these two are the important point. Number 4 is we have assumed constant volume combustion in case of SI engine, and that is why what we did, we have assumed that whenever piston will be reaching at TDC, volume will remaining same and entire combustion will be completed. This is not the case, because of the chemical delay which depends upon the chemical composition of the fuel itself. The fuel itself require a finite time to complete the combustion. Not only that, maybe while we are when we are switching when we are igniting the spark plug by switching it on, then it requires a finite time, and for that we are approximating that we should switch on the spark plug when piston is little bit away from TDC, and by the time when piston reaches at TDC, that time entire combustion will be complete. This is again an approximation. It is not possible that the movement of the piston is very spontaneous. It is not possible that piston will be there for a while and the entire combustion will be completed and then piston will come back from TDC. It is not the case. So the movement of the piston is spontaneous, and we cannot ensure that the entire combustion will be completed when piston is reaching exactly at TDC. I mean volume will remain constant. This is not the case, and that is why what is done, spark plug switch, the spark plug switch is on when piston is little bit away from TDC, and we need to give some certain amount of time only to take into account the chemical delay, also the time required to switch on the spark plug, etc. This is all about the this is constant volume combustion. This is constant volume combustion. For SI engine and constant pressure combustion for CI engine. So this is the case. Now even for a CI engine we are approximately constant pressure process, and what we are doing, that when piston is at the rate of the compression stroke, when piston is away from TDC, we try to ignite, we try to spray fuel through fuel injector, and we assume that by the time entire fuel will be accumulated over the entire fuel spraying will be completed, by that time piston will be reaching TDC and again travelling back from TDC and entire combustion will be completed. So how we can ensure that pressure will remain constant, because maybe when you are spraying certain amount of fuel at the beginning, rather at when piston is little bit away from TDC, the first part or the first phase of the fuel being sprayed, they might take part in the combustion, and because of that combustion pressure will rise and the pressure might change inside the cylinder. So the pressure will remain constant inside the cylinder. It is again an approximation. Since we require finite time for spraying the fuel, so the first part of the fuel being injected into the cylinder, they will take part in the combustion, and because of what, we will have a high temperature and pressure. So if the pressure changes, how we can assume that the pressure will remain constant inside the cylinder to complete the entire combustion, and this is again an approximation for the SI engine. Third thing is exhaust blowdown. What we do, fifth is constant volume blowdown. Constant volume blowdown, that is we have assumed for all three different cycles, diesel, dual and auto. So we are assuming, what do we do? We try to open the exhaust valve when piston is little bit away from BDC during end of the expansion stroke, and by opening exhaust valve we are trying to reduce the pressure inside the cylinder, so that in the next stroke when piston is coming back from BDC to TDC during exhaust stroke, it will encounter less resistance. And to do that, we try to remove certain amount of combustion product before piston reaching at BDC during at the end of the expansion stroke, and we open the exhaust valve. While we are doing so, then how can we assume the volume will remain constant? Because the moment when we open the exhaust valve, certain amount of combustion product will go out from the cylinder and volume will no longer remain constant. Not only that, while we are doing so, then we are again try to underestimating the thermal efficiency, because before piston reaching at BDC during end of the power stroke, we are opening exhaust valve and we are allowing certain amount of combustion product to go out. That means we are not allowing that amount of combustion product to do work on the piston face. That means eventually we are sacrificing certain amount of work output from the system. So all these approximations are not true sense occurring in a real engine, and that is why, although we are doing those approximations only to simplify our analysis, but all those approximations introduce error in the analysis, and as a result of which maybe the thermal efficiency what we are getting from different from auto, dual and diesel cycle, from considering air standard analysis, that will give us the indicated thermal efficiency, but the efficiency in the real case will be somewhat different than what predicted by the air standard analysis. So with this I stop my discussion today, and I will continue my discussion in the next class. Thank you very much.